Welcome. We're going to talk about waves today. Kind of a topic that's definitely applicable to everyday life. We see sound waves, light waves, electromagnetic waves every single day, and hopefully tonight you'll come away with a little better understanding of what they are. So, to begin, waves in general, whether they be water waves like the one down here, or whether they be light waves or sound waves, they're oscillations and they transport energy. It's kind of the big thing here is that energy is transferred, okay? That's the whole point of a wave. Now, we can break waves into two basic categories, being mechanical or electromagnetic. Now, electromagnetic is an entire day itself, so we'll spend that in a whole other unit. So today, we're going to focus on mechanical waves, or waves that require a medium. And what a medium is something to travel through. So over here, an ocean wave, the medium would be good old H2O, some water. Sound waves travel through air. But electromagnetic waves, on the other hand, they don't require this medium, so they can travel through empty space itself. So light waves can travel through empty space because they're electromagnetic, but mechanical waves, sound, water, and earthquakes, they can't. They require that medium. So let's go on to talk more about mechanical waves. We have two types of mechanical waves, and the first that we're going to talk about is the transverse wave. And kind of the key part of this word is the prefix trans, which means opposite. So it says that oscillations are perpendicular to the direction of motion, would be the book definition of it. But I really like this picture over here, if you take a look at this one, because it describes it pretty well. And we see a really good transverse wave. This is kind of the wave you guys typically think of, kind of the crests and troughs. And what this picture is trying to show you is this guy's hand is going to move up and down. So the motion is up and down, but the wave oscillates perpendicular to that. So up and down motion, but oscillation is to the right there. So the particle motion actually goes up and down again, but the energy itself goes this way. So that's transverse. They're opposite of one another. Many of our common waves act this way. We've got light waves, water waves, earthquake waves, and then we're going to learn tonight about how to pick these pieces apart of the transverse wave. So let's go look at a transverse wave. And we see that a transverse wave can really be broken down into many different parts. So the wavelength is probably one of the most important parts. So the wavelength can go from crest to crest. You could say from trough to trough would be a wavelength here. Okay. You can even say from the resting point to another resting point would be a wavelength. But most importantly, it's from one point of the wave to another point of another wave. But it has to be the same point on each wave. We can look at the amplitude of the wave, which is really the distance between the resting point and the height of the wave, which we call the crest. Or we can look at it this way over here. We can look at it the difference from the resting point to what we call the trough of the wave, which is the bottom of the wave. So we have resting point, which is this dotted line in the middle. We have our crests at the top of our wave. We have our troughs at the bottom of the wave. We have the amplitude, which is from resting point to crest, or resting point to trough. And we have our wavelength, which is crest to crest, trough to trough, or resting point to resting point. So a lot of vocabulary at once, but it should make pretty good sense. In contrast to a transverse wave, we have what's called a longitudinal wave. So prefix here being almost long, right? And this time, the particle motion and the energy are going in the same direction. So if we look at this picture here, my person's hand is moving to the right. You can think of this kind of like a slinky. And all of the particles are going to move to the right. And in this wave, we don't really see that nice motion like that. We see it more represented like this in a series of what we'll call compressions and rarefactions here. Okay? So transverse waves, opposite movement. Longitudinal, the particle moves in the direction of the energy. Some examples of that would be sound waves and earthquake waves also, but earthquake P waves, which we'll talk about. I really like this picture here of the longitudinal wave at the top because this shows you how sound travels as a longitudinal wave. And on the left side of this picture we have our speaker. And what the speaker does is it really works as these kind of compressional phases where it bounces up and down, right? If you ever look at the speaker without the cloth over the top, you can see it vibrating. What that does is that causes the air molecules here, you'll see, to begin to compress against one another. And as this guy bounces, these compressions occur, and all of a sudden we have these compressions of air making it to our ear, and eventually we interpret this as sound. If we look at this, once again, like I was saying on the other slide, we don't see this as our wave anymore. We see our wave as a series of compressions here and rarefactions here. So rarefaction and a compression, and a series of those would be one singular wavelength. So compression to compression. So make note of those. Compressions is where the medium is pushed. And rarefaction, not fraction, take note of that please, is where the medium is spread further apart. And you can see that again down here in the same picture. We'll show you some examples of these tomorrow with some wave motion software we have. Now we'll get down to a little bit of the math. Math is pretty simple. Once again, it's just three variables. We have lambda, which is this symbol here, equals velocity divided by frequency. Now, lambda is your symbol for wavelength, which is measured in meters, which makes sense because wavelength, you can think length here, would be a distance, so meters would be appropriate. And velocity, of course, is meters per second, which is how fast the wave is traveling. And frequency is really the one you probably don't know, which is measured in hertz, which I'm sure you've heard before. And it's how many full wavelengths pass a certain point of time per second. So how many full wavelengths per second are occurring in that wave. If we look at energy in waves, we can kind of look at it two ways. Energy is determined by the amplitude. In other words, the higher the amplitude we see here on our right, because this really steep amplitude here, this has much higher energy when compared to this wave right here, which has a lower amplitude. We can also look at the frequency. And remember, when I say frequency, I mean the number of waves in a matter of time. So let's say that these two graphs occurred over a time of 1 second. And if I wanted to count how many waves were here, I would say that would be one wave right here. This would be 2 waves. And that's about 3 waves. So that's 3 waves per second. That's terrible handwriting. Or 3 hertz is how we would equate that. Now if I look at this guy, I'd look at here's a wave. There's another wave, another wave, another wave, another wave, and so on and so forth until we get 1, 2, 3, 4, 5, 6, 7, 8, about 9 waves per second again, or 9 hertz. So you can see that looking at a graph, if I have a period of time and I can determine how many waves there are, I can easily determine the frequency or the hertz. This is a cool little demo we'll show you tomorrow. You're more than welcome to go take a look at it at that website. Then the last thing we'll talk about is the Doppler effect. And this is something that you've seen before, or heard before I should say. It's the change in frequency of a wave due to the position, due to the relative motion between source and observer. It's pretty much what we're saying is that as an object making noise moves closer to you, the pitch of the noise will increase, and vice versa. As the object making noise moves away from you, the pitch of the noise will decrease. And I have some pictures on the next slide to show this to you. Now, I like this one the best down here because the kid looks really goofy, but it also explains it really well. Let's say that you're standing in the middle of the street, well, on the side, because we don't want to stand in the middle, you'll get hit. You're standing on the side of the street, and all of a sudden you hear an ambulance coming. As that ambulance is approaching you, the closer it comes, the louder it will appear. And you can see what the kid is hearing right here, and you can see this really high frequency, a lot of cycles per second, and that sound appears louder. But if you really think about it, it's not actually getting any louder. What's happening is the ambulance's movement is compressing those waves tighter, as you can see. In contrast to that, as the ambulance continues to pass you, you'll see that on the back end, we have kind of a spreading apart of the sound waves. So with a moving object, the sound being produced is not moving to each side evenly. And because of that, we see this series of kind of breaks between the waves, and on the front end of the object, or wherever it's moving, we see those series of compressions. So long wavelength, small wavelength, high frequency, low frequency here. And that's essentially the Doppler effect. Exactly why a police car would sound louder if you were here when compared to here. But it's not actually making any difference in its sound waves. We just see the compressions here and not out here. So that's the Doppler effect. We'll have some demos for you tomorrow from this website. You're more than welcome to look at them. That's all for tonight, guys.